Okay, welcome to this quick video on calculating oxidation numbers. Okay, so what we're looking for you to get out today are the following. Recall the oxidation numbers of elements and common species. I apply these oxidation numbers to different compounds and ions to deduce the oxidation numbers of atoms involved in these substances. Use oxidation numbers in IUPAC names and deduce the formula of an IUPAC name. Okay, so what you're familiar with from GCSE are the ideas of oxidation and reduction. Oxidation is the loss of electrons, reduction is the gain of electrons. And this equation here shows quite common a common redox reaction. This is a reaction where both oxidation and reduction has occurred. However, looking at this equation, it is very difficult to see which species has lost electrons, which species has gained electrons. Now you might be able to work this out by using your ideas of ionic bonding, but if we had a different system, that would make it a lot simpler for us. Okay, so the rules for oxidation numbers. In a chemical formula, each atom has an oxidation number. Okay, it is just something that we as chemists assign. It's not an actual thing. And in essence, this oxidation number relates to the number of electrons used by an atom to bond to another atom of a different element. And that's really important that it's a different element. So we use the following set of rules. Now in your notes you have a much simplified version of these rules. So do feel free to pause the video and take a longer look at this. Any uncombined elements, now by that we mean an element which is not combined with another element. So the confusion is if you've got something like O2, well, the oxygen atoms are combined, but they're combined to atoms of itself. So any element in its ordinary elemental state has an oxidation number of 0 by definition. Oxygen, common when it's combined to other elements, will 99.99% of the time have the oxidation state of -2. Okay, there is an exception. It's peroxides such as H2O2. When hydrogen is combined to other elements, it will always, pretty much, have an oxidation number of +1. There is only one exception, and that is metal hydrides. So sodium hydride, lithium hydride, etc. Next, the charge on a simple ion. So if you've got a species such as sodium fluoride, well, you know that in an ionic compound, sodium will have the charge +1. If it's a calcium in, say, calcium oxide, you know that calcium has a charge of +2. So therefore, the oxidation number is the same as the charge. And again, for the non-metals such as chloride, iodide, bromide, if you know that the charge on the ion is a 1-, then the oxidation number is -1. When fluorine is combined to any other element, always -1, always -1. And then we've got some different rules here. So group 1 elements, when they're combined, always +1. Group 2 elements, always +2. Group 3 elements, when they're combined to something else, always +3. Groups 7, 6, and 5, these depend on whether they're like simple binary compounds, so there's just 2 elements such as calcium chloride, phosphorus tribromide. So if they're simple binary compounds, then they'll have an oxidation state of -1. If oxygen or fluorine is also involved in the bonding, then you've got to work at the oxidation state. Similarly, group 6 should have oxidation number of -2, but it could change if there's oxygen or fluorine involved. And group 5 elements, -3 typically, but again, it depends on which other elements are involved. So again, it does get quite complicated. And here's just a way to use your periodic table. So groups 1, group 2, group 3. Group 4, we've assigned here a +4, but it can be variable. And again, 5, 6, 7, usually -3, -2, -1, but they can change as well. Transition metals commonly have an oxidation number of +2, but this does change. Okay, so how to calculate the oxidation number of an unknown element. So if I just get my pen. So if you've got potassium bromide, now you know that potassium is in group 1. So therefore, when it combines to bromine, it's going to have an oxidation state of +1. So what we can do is we set this simple equation up, which is the sum of the oxidation numbers equals the charge. So in this case, we've got +1 plus our oxidation number equals 0. Okay, so what we need to do then is subtract 1 from both sides to get rid of this +1 on this side. And 0 minus 1 equals -1. So our oxidation number is -1. In this example here, carbon dioxide, we know that when oxygen's combined, it's got an oxidation state of -2. And we've got 2 lots of -2. Okay, so we've got our oxidation number of carbon plus -4 equals the charge, which is 0. So we'll simplify that. Ox -4 equals 0. So then your oxidation number is equal to +4. Calcium chloride, you know that it's calcium's got an oxidation number of +2 because it's a group 2 metal combined. Now we've got 2 lots of chlorine. Okay, so what we would do here is we would say 2 lots of our oxidation number. We're going to subtract both. We're going to subtract 2 from both sides, and then we'll divide through both sides by 2, so that our oxidation number equals -1. Okay, again, similarly here for dichromate, this formula of an ion you do need to know. We've got 7 oxygens combined -2, so that gives us a grand total of -14. We've got 2 chromiums, and we've got a charge of -2 this time. So now we set it out that we have 2 oxidations, or 2 chromiums. Going to add to that -14, and that equals our charge of -2. Add 14 to both sides. Divide both sides by 2. And we get that our chromium oxidation number is equal to +6. Okay, have a go at this one yourselves. Pause the video, have a go at this one yourselves, and I'll reveal the answer in a second. Okay, so here's your little test. You can have a go at these ones. Okay, check them with your answers in the booklet. Okay, so the next bit is here. So using oxidation numbers to name transition metal compounds. Okay, so I said a few minutes ago that transition metals typically have an oxidation number of +2, but they can have different oxidation numbers. And this becomes very important, especially when we're trying to identify our different transition metal complexes in year 2. So the formula FeCl2 is iron chloride. FeCl3 is also iron chloride. Okay, but what we do is we call these iron 2 chloride because the oxidation number of the iron here is +2, and this one here is iron 3 chloride because that's an oxidation number of +3 there. Okay. Convince yourself that those are the correct oxidation states, remembering that a simple chloride has an oxidation number of -1. So, looking at the formula here, CuO, that has been given the name copper 2 oxide. So, using the analogy from above, you should be able to identify that copper has an oxidation number of +2. And try and fill in the rest of the blanks now, okay, using the examples here around you. We can also use IUPAC names for naming molecular ions. Now, a molecular ion is an ion which is based on atoms covalently bonded together. So the the common ones you encounter are sulfate, nitrate. Here we've got the formula. So we've got 2 ions here which are called sulfate ions. These 2. Now that is called sulfate 6. This is sulfate 4. So again, just be familiar with your so let me just change that. Please do be familiar with your Roman numerals. And so that tells us that in this ion, the oxidation state of sulfur is +6. The oxidation state of the sulfur here is +4. And then here we've got nitrate 5, which is an oxidation state of +5. So could you then write what the nitrate oxidation number in Roman numerals is here? And then could you apply these to these species down here? Just a quick word on the naming. All of these molecular ions end in 8 because they have oxygen present. Okay, so that is something to bear in mind. You know, what's the difference between a sulfide and a sulfate? Sulfur ate all the oxygens, so it's got 3, 4 oxygens, however many. Okay, in the next video, I'm going to explain to you how to calculate the formula of a molecular ion. Thank you for watching.